Welcome to a deep dive into the statistical foundations that are absolutely crucial for anyone venturing into machine learning. Today, we're going to demystify core statistical concepts, showing you exactly how they underpin effective data preparation and understanding for your ML models. Building an intuitive grasp of how your data behaves and interacts isn't just academic, it's essential for smart feature engineering and making informed model selections. At the heart of understanding data lies the concept of probability distributions. Think of a distribution as a map that tells us how frequently different values appear within a dataset. It's the visual fingerprint of your data, revealing patterns and tendencies that raw numbers alone can't convey. Grasping these patterns is your first step towards truly understanding your data. Perhaps the most famous distribution is the normal distribution, often called the bell curve. It's symmetric, with most data points clustering around the mean, and fewer points as you move away from the center. Many natural phenomena and even errors in measurements tend to follow this distribution. In machine learning, it's often an assumption for many models, such as linear regression, and understanding if your data approximates normality can guide your pre-processing choices. But what if your data isn't perfectly symmetrical? That's where skewness comes in. Skewness measures the asymmetry of a distribution. A positive skew indicates a long tail extending to the right, meaning the majority of data points are concentrated on the left. Conversely, negative skew means a long tail to the left, with most data on the right. Recognizing skewness is vital because highly skewed data can mislead models that assume symmetry, often necessitating transformations like log or square root. Beyond symmetry, we also need to consider kurtosis, which describes the tailedness and peakness of a distribution. High kurtosis means more extreme outliers and a sharper peak, while low kurtosis suggests fewer outliers and a flatter peak. Datasets with high kurtosis can indicate a higher risk of extreme values impacting your model, making robust scaling or outlier handling techniques particularly important. So, why do these distributions matter for ML? Because many machine learning algorithms make assumptions about the underlying distribution of your features. For instance, some models perform better with normally distributed inputs. Identifying skewness or high kurtosis helps you decide if data transformations are necessary to meet these assumptions, improve model performance, or prevent sensitive models from being unduly influenced by outliers. It's about getting your data in the best shape for learning. Now, let's talk about one of the most powerful theorems in statistics, the Central Limit Theorem, or CLT. In simple terms, the CLT states that if you take sufficiently large random samples from population, the distribution of the sample means will tend to be approximately normal, regardless of the original population's distribution. The larger the sample size, the closer the distribution of sample means will be to a normal distribution. The CLT's relevance in ML is profound. It underpins many statistical inference techniques and helps justify why certain models work even when the raw data isn't normal. For example, if you're building a model that relies on calculating means across subsets of data, the CLT tells you that those means will behave predictably. It also implicitly supports techniques like bootstrapping and cross-validation, where you repeatedly sample from your data to estimate model performance. Moving on, we come to covariance, a measure of the joint variability of two random variables. It tells us whether two variables tend to move in the same direction. A positive covariance indicates that as one variable increases, the other tends to increase too. A negative covariance suggests they tend to move in opposite directions. A covariance near zero implies little to no linear relationship between them, while covariance tells us the direction of the relationship. Its magnitude isn't easily interpretable because it depends on the scale of the variables. This is where correlation steps in. Correlation normalizes covariance, giving us a standardized measure of the strength and direction of a linear relationship, typically ranging from -1 to +1. A correlation of +1 means a perfect positive linear relationship, -1 means a perfect negative linear relationship, and 0 means no linear relationship. In machine learning, covariance and correlation are invaluable. They are fundamental for feature engineering, helping you understand which features might be redundant or how they might interact. High correlation between independent variables, known as multicollinearity, can severely impact models like linear regression, making coefficients unstable and difficult to interpret. Identifying these relationships early can guide feature selection or regularization techniques. Ultimately, having a strong intuitive grasp of data distributions, the Central Limit Theorem, Covariance, and correlation empowers you to ask the right questions of your data. It moves you beyond simply running algorithms to truly understanding your dataset's personality, enabling more effective pre-processing, smarter feature engineering, and ultimately, building more robust and insightful machine learning models. Keep exploring, keep learning, and your models will thank you for it.